Hello everyone, my name is Kanna, a B.Tech student in Biomedical Engineering at IIT Hyderabad. This presentation is about my summer internship project on building a washing machine simulator using the PIC16F877A microcontroller done as part of my Embedded Systems Internship at Emertxe. Let's overview this. So this internship focused on embedded systems and microcontroller programming. So in the first phase, we actually learned how to we program like embedded C programming. We just learned through that, and soon after that, we learned about the microcontrollers. How do we use them? How do we read the schematics and that stuff? And soon after that, we started to simulate the washing machine concept as part of our project. So this project emphasized the real-time system design and automation logic. So goals of this internship. So my main goals were to get hands-on experience with embedded systems, understand the internal architecture of the microcontrollers, learn how to read board schematics, explore simulation tools for testing and enhancing my debugging and hardware abstraction skills, which were basically given by Emertex's internship. So coming to the what is an embedded C or what is an embedded system? Let's understand. So embedded C is a programming language used to program microcontrollers. It is an extension of C language with hardware control support. So it's used in direct interact with ports, pins, timers, etc. So which enables building real-time systems like washing machines, alarms, robots, etc. So now let us see about the embedded system overview. So any system that performs a specific task using hardware and software and which does not need any full operating system is considered as an embedded system. So coming to the examples of the embedded system, so you can see automatic gate opener, washing machine, smartwatch, fire alarm system, and many more. So there are like categories of embedded systems. So in the categories, the one is the standalone, which is like works independently, like washing machine, and networked, which is like connected via the network, like Bluetooth, Wi-Fi, and stuff, which is like the smart home kind of embedded system. So coming to the real time, which is like which must respond quickly. Example like the medical field, it's a pacemaker, so which basically responds quickly and which is like a real time embedded system. So coming to the mobile, which is like portable devices like fitness bands and stuff, these are comes under embedded system, like mobile embedded systems. Coming to the hybrid, which is like a mix of all these types of systems, is like an example like if you take an electric Tesla car, this comes under the embedded system. So coming to memory in embedded systems, so they're like RAM and ROM. So in RAM, which is like a temporary storage, which will be erased when power is off. So this is like a RAM, which is volatile. So coming to the ROM, which is like a non-volatile, which is a permanent memory, which like if it is written, then it is stored permanently. So coming to the types of ROM, there are like PROM, EPROM, EEPROM, and flash memory. So what is PROM? So it is PROM is like the programmable ones. Once you like you can program once. And EPROM is like it is erasable using UV light. If you use a UV light, then it is erasable. And EEPROM, which is like electrically erasable byte-wise. So it will erase byte-wise. So coming to the flash memory, it is erasable block-wise, used in password lockers. Right. So next, let us see what is a microcontroller. So a microcontroller is a compact integrated circuit that contains CPU, RAM, ROM, input-output ports, and timers. It is designed to control electronic devices. So for this project, we used a PIC16F877A microcontroller by Microchip. So a popular like 40-pin microcontroller for embedded applications. So you can see this is the schematic like the diagram of this PIC16F877A. You can see there are like 40 pins. Each has each is connected to other component and the voltage is voltage sources. So this is a 40-pin microcontroller from Microchip. It basically has 5 ports A, B, C, D, and E, which is used in industrial and home appliances. So we use it to simulate our washing machine logic. So you can see the operating frequency, which is like 20 megahertz, which we have used, and flash program memory is 8K, and data memory is 368 bytes, and EEPROM that we have discussed, which is 256, interrupts 15, the ports 5 ports, timers 3, capture and stuff that is 2. So serial communication is MSSP and USART, and parallel communication is PSP. So it has 8 input channels and 2 comparators, and it has 35 instruction set. So packages 40 pin PDIP. So now let us see the tools we have used for building this uh, washing machine project. The first one is the MPLAB XIDE and the PICSimLab. So in the MPLAB XIDE, it's a code editor and a debugger. So we basically write the embedded C program in this. So now once we have written the code, now the machine should understand it, right? So to make it understand, we need a machine code. So to get that machine code, we used XC8 compiler, which converts embedded C to machine code, which is like a hex code file. And we take that hex code file and we load it in this PICSimLab. So this which is a simulator, this is basically a simulator, which is like a not a physical hardware, which is like which runs in our software. So you can see this is the CLCD display, and this is the fan. This is the buzzer. The small is the buzzer switch, and this is like we made it as switch 1, and this is switch 4. This is switch 5, and this is switch 6, and this is our microcontroller. You can see it here. So this is basically the overall PICSIM interface. How does it look and stuff. So now let's see this. We'll break down the components and stuff. So these basically these are like the switches, right? So these are like the tactile switches, which are using like pull up and pull down resistors. So these have two detection methods. One is like the level triggering, and the other one is the edge triggering. So level triggering is based on the voltage level, which is like high or low, and whereas edge triggering is based on the signal change, like whether it is rising edge or whether it is falling edge and stuff. So coming to these have a small thing to handle. One is the bouncing effect. So what is this bouncing effect? So where multiple signals occur from a single press. So like when you press the switch continuously, there are like multiple signals coming. So which can cause multiple detections, which we doesn't need it. So to handle this bouncing effect, we basically use fixed delays. Like you use a delay, like when you press a switch, wait for this time until this time, so that it is in an on state. Like that, you basically program that. So you can see this is basically a representation of the bouncing effect. So we use the like software debouncing techniques to remove the bouncing effect. So coming to the timers. So timers help track time or create delays. The microcontrollers includes 8-bit timers, right? So we have seen in that table, which is the 8-bit timers. So we calculated the timer ticks using the formula Q equals to 4 divided by the frequency of the oscillator, that is 20. So 20 megahertz. So I also used the prescalers and postscalers to fine tune timer performance and set up interrupts for time sensitive tasks. So you can see Q equals to 4 by frequency of the oscillator, which is 20 megahertz. It's like Q equals to 20 nanoseconds. So so ticks equals to overflow time equals to ticks into Q, which is 256 into 200 nanoseconds. So it's like the 51.2 microseconds. So prescaler, which is like increases tick time, which is like slower time, and post-scalar ISR triggers after several overflows. So interrupts are triggered on an overflow or an external event. So interrupt service route, which is like are used interrupts are used to respond immediately to events like timer overflows or external signals when triggered. an ISR or interrupt service route is executed. It's important to manage flags and consider interrupt latency for responsive design. So we also use the CLCD, which is like the character LCD, liquid crystal display. So a character LCD is a display module used to show alphanumeric characters and symbols. So these are like many common types in this where we have used this HD 44780 16 into 4, like it is like 16 characters per row and 4 rows. So it supports alphanumeric characters and is commonly used for embedded system for displaying the real-time data display. Right. Now the overall workflow of this project. So which basically how this is the starting screen. When you press the key 5, it will power on and shows the screen power on in washing machine, and you get the first page like get select options, which is like a daily, heavy, delicates, and there are few options. So to navigate through options, you basically single press the switch 4, and to select this option, you basically long press the switch 4. So when you long press this option, you get you navigate to the water level. So now we again in this also you can basically switch for long press to select, or you can use a single press to navigate. So I again long press this and again navigate to this. Now if you press switch 5, then you get start and you go to navigate to this. And if you press switch 6, then you again navigate to this washing program screen. So again, if after pressing switch 5, there's a time allotted to this modes like daily and auto. There are like 41 seconds. You can make it a minutes in the real time uh, simulation. I mean, in real time building. So after this, the screen shows up, and soon after a delay, then the screen shows up showing the wash time and like how much time is the thing, and start and pause. So this got started, and this function gets changed like wash, rinse, and spin, which we allotted a specific percentage times for each of the function. And suppose uh, if you want pause it, then you press switch 6, then the fan gets off and buzzer gets on and timer gets off. And again, if you want to start, you press the switch 5. So again, it starts and it shows rinse and spin, and the program gets completed. Suppose suddenly the door is open. So to simulate this door is open, we use switch 1, which basically when you press it, the door is open. So it asks you to please close the door, making the buzzer on. So after that, you navigate to the program complete, remove clothes uh, after the whole function is completed. Now let us see. You can see we press the switch 5. So basically this is the switch 5, and we long press this switch 3, uh, like single press to navigate through the options. So we basically long press this to select the daily and the water level. So we basically selected long press the auto. So next we basically want to start the thing. So we press switch 5. So the time got displayed. The time is decreasing and the fan is on. And when you press switch 1, door is open, and you want to pause it. So you press switch 6. It is paused. Fan is off. Again, if you want to start, press switch 5. So it's getting run. You can see this is the buzzer, this is the fan, this is the CLCD display. See, you can see it got changed to rinse after some time. Again, it got changed to spin. And now program completed, remove clothes. This is the overall simulation of the washing machine project. You can see this is the clock which is like 20 megahertz and HD 44780 16:4 LCD display and the temperature and stuff. Coming to the code stuff, we used MPLAB XIDE, right? So in the MPLAB XIDE, you can just see this, which we had the header files to define the macros, and we basically defined the functions. This is the function, like washing machine definition, like what are the programs that we are doing, what are the water level that we are using, what when switch 4 is pressed, what we need to do, when switch 5 is pressed, what we need to do, what is the time that need to be allotted a spin or like each program that has been written in this code snippets. So, so we successfully simulated the washing machine controller using the PSC 16 F877A. So I basically learned embedded C, timer, ADC converter, input output ports, like debugging using the simulation tools, improved understanding of the embedded workflows and system design, like how do we read it, like the overall understanding of the embedded systems. So it has been wonderful doing this simulation and working with this project and learning the embedded systems. So thank you for taking the time to listen to my presentation. I'm truly grateful to Emertech for providing me this opportunity to work on the real-time embedded systems. So this internship has been a valuable learning experience, helping me grow both technically and professionally. Special thanks to my mentors and peers for their guidance and support throughout the project. I look forward to apply these skills in future endeavors. Thank you once again. Thank you. Signing off.